let's wrap up our whole parametric polar unit by looking back at a bunch of stuff we've seen and maybe some stuff we haven't seen yet, and think about, would we model this with parametric equations? Would we model it with polar? Let's ignore the fact that if you have polar, you can turn it into parametric. Let's think more like what's the natural way to do stuff. And think about why would one situation be more naturally modeled with parametric or polar or something. So the first thing we'll look at, we looked at it in terms of parametric. This is how we introduce parametric stuff. This is flight tracking data from an airplane that came in this way and did a loop and then did another loop. These are horizontal loops, not vertical loops. And then came over here and landed in an airport. So would you say parametric or polar is a more natural way for that? What about the point of view of the airport, which might have radar that's turning a dish around and saying, is there anything out this way? If so, how far is it? Is there anything out this way? If so, how far is it? It's another way to think about things. Let's look at some other stuff. We talked about spirographs. So would you model a spirograph curve as a parametric curve or a polar curve? Here's something I did at the end of a Calc 2 class one semester when we were face-to-face. So I've got an orange string hanging from two spots on the ceiling, forming a V, and then an orange string hanging from that, and then a water bottle that's full of salt with a little hole in the cap so it's leaking out. So if this swings back and forth, it's basically a pendulum with the length from the ceiling to almost the floor. But if it swings side to side, then the pendulum only has a length from here because it can't move side to side at this point of the V. So let's show a video of that. It's nice and calming. So we get this nice curve. Would you model that curve as a parametric thing or a polar thing? And you might think, well, spilling salt on the floor in a classroom is kind of fun, but what you really want to see is something bigger. By the way, the name for this is called a Blackburn pendulum, or sometimes a double pendulum. If you wanted to see something bigger, one day we threw some string over the house and tied it to the roof of the garage, and then hung a string from that, and, here we go. And had an old milk jug with a hole in the cap and put some water in it, so it traced out a pattern on the ground here. So that's also a double pendulum or a Blackburn pendulum. We have an amazingly impressed kid here. I'm not sure why this kid is not more impressed, if that would be possible. So just some fun with polar or parametric formulas there. Here's another fun device someone made. So this thing is the size of a room, and it's got two sets of big weights that move back and forth as pendulums, and then a pen connected to that. Another interesting fact, there's something called a Gulosh pattern, and that's like the fine detail scroll work on currency. Here's a detail from a US $1 bill, and the way they made this apparently is they had some big machine, kind of like what we just saw, that traced out a pattern like this. So would you say that's more of a polar curve or a parametric curve? All kinds of interesting things. And then if that wasn't fun enough, let's talk about rides at amusement parks. Here's one I saw and thought, I should show my parametric and polar students about that. This one's a little interesting because the people themselves decide how quickly to spin their little cup. So there's that one, and then one that's possibly a little more exciting. Would you use parametric or polar for this one? All kinds of interesting modeling things to think about. So let's see when they get going even faster. Nope, it's not fast forwarding. Anyway, parametric and polar modeling, lots of fun.